In this video I'm going to give you some hints on how to solve the merger simulation section in the notebook. And the first part to solve that section is to solve for a Cournot model. So we're going to look at a very simple case. So we're going to have the simplest demand function that we can think of, equal to 1 minus Q, where capital Q basically means total output on the market, so the sum of outputs of all the firms. And we're going to assume that each firm's cost function is basically the simplest one, it's constant marginal cost. Yeah, so this is the setup that we're going to be working with. And now in Cournot equilibrium, each firm is going to choose its output level such that its profits are maximized given the equilibrium choices of the other firms. So the way we can write this is we're going to say that Qi is equal to the argmax over x, where x is the choice of output of firm I. And then we're going to get first the price of firm I, so that's 1 minus x minus the sum over all other firms not equal to I of Qj. So this part here is basically the price that the firm I is going to get if it's going to choose output level x. So we need to subtract its cost level from that, and then we multiply by x. So this is the optimization problem for firm I. Given the output levels chosen by the other firms, it chooses its own output level x here, which maximizes its profits. So this is called the reaction function. The first part is to model this reaction function in Python. So we're going to do that. So I'm going to define a function reaction, which is a function of the output level that's chosen by all the other firms together. So it's the sum of their output levels. And we have the cost level of firm I itself, C. So what it returns now is the optimization over the profits of that firm, firm I. Now the problem is that in Python we don't have a maximization routine, so we're going to use a minimization routine, fmin bound. We're going to define a lambda function. This is then going to be equal to minus profit, so it's going to be minus x times, here we're going to get the same thing, first price, Q, other, minus x itself, minus c. When we use fmin bound, we give the bounds between which the routine is going to look for the optimum, so that's, we're going to specify that's going to be between 0 and 1, because given the price function that we're using, we don't expect output to be bigger than 1, because that would lead to negative prices, and outputs cannot be smaller than 0 because they're quantities, so it's going to be between 0 and 1. And we're going to specify full output is equal to 1. So if you want to see what that does, look at the documentation. So you simply use sp optimize fmin bound with a question mark, and it will tell you what it is. And basically from this optimization routine, we want to have the first element of what it returns. So this is the reaction function. So to get an idea of what's going on, let's plot this reaction function. So I'm going to specify a range for Q. And it's going to be equal to, we use numpy, a range. We're going from 0 to 0.6 with steps of 0.1. And then we're going to plot range Q, and then the reaction function, so that's going to be reaction of Q, and we're going to assume that the cost level of the firm is 0 for Q in range Q, so we're using list comprehension here. So let's see what this looks like. Oops, we made a mistake somewhere. Oh yeah, so we didn't get the completion here, so it's going to be range Q. And here we have it. So it's a downward sloping line, so that's the reaction function of one firm, and of course you also want to have the reaction function of the other firm. And that's actually pretty easy to do in Python in this symmetric case, so I'm going to copy this. And I'm going to put it in front of this one, so basically we switch the x and the y, and now we have two lines showing us the reaction functions. So the equilibrium is going to be when we're at this intersection point of these two reaction functions. So basically what you can do is you can add an x label. So let's say that on the horizontal axis we're going to use LaTeX. We're going to put Q1. So that's why we use the dollar signs to get LaTeX. So on the other axis I'm going to put Q2. Yeah, and I leave it to you to also create the legend. So you can specify here, label is reaction function firm, and leave it to you to figure out which reaction function this actually is. And similarly for the other one. Yeah, so if this is 1, then the other one is 2, or this is perhaps 2 and this is 1. I'll leave that to you to figure out, and then you can have the legend as well in the graph. So the thing that we need to do now is to calculate this equilibrium point, this intersection point of these two lines, of these two reaction functions. And the way we do that is we're going to define a function called fixed point. And that's going to be a function of the vector Q. And we're going to do this for a duopoly. So Q is going to have two elements, and C is going to have two elements as well. So that's the output level for each firm. So that's the first and second element of Q, and it's the cost level of each firm. So it's the first and second element of C. So this function is going to return a list. And the first element is the difference between Q0, so that's the output level of the first firm, and its optimal reaction. And its optimal reaction is to the output level of the other firm, so firm 2, but in Python indexed 1, while its cost level is equal to C0. And we're going to have a very similar expression for the second firm, so the only difference is going to be that the second firm is Q1. It reacts optimally to the output level of the first firm, and its cost level is going to be equal to C1. So this is the fixed point, and now if the fixed point is equal to 0, so we're going to be looking for the 0 of the fixed point, it's going to be the case that Q0 is equal to the optimal reaction of the first firm to the output level of the second firm, and Q1, so the output level of the second firm, is going to be equal to its optimal reaction to the output level of the first firm, while its cost level is C1. So indeed that would be an equilibrium. So we're going to use SP optimize, SciPy optimize, and here we're going to be using fsolve because we're looking for zeros. So we're going to need a lambda function here because fixed point has two arguments, and when we use we look for zeros, we only look zeros over output levels, so over x, and we're going to specify the cost levels as both equal to 0, so both firms have 0 cost levels. And then we need to give a starting point to the optimization routine, and since we're optimizing over a two-dimensional vector, our starting point needs to be two-dimensional as well. And when we calculate this equilibrium, so we solve for this fixed point to be equal to 0, it happens at 1/3, 1/3, and if you look here, that seems indeed right, that this intersection point is exactly at 1/3, 1/3.